Hello! With this video, we begin the series on 3 antiepileptic drugs: Phenobarbital, Ethosuximide, and Levetiracetam. The series includes an introductory video. This video, videos on retrosynthesis, and videos on the resulting syntheses. Here we present the systematic names, CAS numbers, structures expressed in 2 and 3 dimensions, for phenobarbital and ethosuximide. Phenobarbital is a derivative of barbituric acid, which is substituted at carbon 5 by ethyl and phenyl groups and does not have chiral carbons. Ethosuximide is a derivative of succinimide, which is bonded to methyl and ethyl groups. It presents a chiral carbon, and the structure shown represents the S enantiomer. Levetiracetam is considered a pyrrolidone derivative with a substituent attached to the nitrogen of the heterocycle, which corresponds to butanamide. It presents a chiral carbon with S configuration. Before the creation of phenobarbital, bromide salt therapy, which is very toxic, was used. Barbituric acid was synthesized in 1864, which by itself is inactive. Subsequently, barbital was created, which is primarily a sleeping aid, and with the idea of continuing to obtain drugs with sedative activity, phenobarbital was generated. Subsequently, its antiepileptic properties were discovered by chance, so since 1912, it has been used mainly as an antiepileptic. And after more than a century, it is still used and is included in the World Health Organization's list of essential medicines. Furthermore, from changes to the structure of phenobarbital, we can see the generation of other types of antiepileptic drugs when considering a contraction of the 6-membered ring of phenobarbital by the exclusion of the indicated carbonyl. It can be visualized that a 5-membered ring corresponding to a substituted hydantoin is obtained, specifically mephenetoin, and by substituting the indicated nitrogen atom with carbon, we obtain a substituted succinimide, in this case, ethosuximide, whose synthesis was reported in 1927, but it began to be used clinically only in 1960. In levetiracetam, we can visualize its structural relationship with the neurotransmitter GABA, although levetiracetam does not behave as an agonist or antagonist of GABA. Butyrolactam, which in general can be considered inactive and has important applications in polymer chemistry. By derivatizing its nitrogen pyracetam is obtained, which is used as a memory enhancer, drugs known as nootropics, and by adding the ethyl group to the chain of piracetam, you obtain levetiracetam, which is used as an antiepileptic. The 3 drugs are used as antiepileptics, and although their mechanisms of action are different, it can be said that the common strategy is to reduce the excess neuronal electrical activity that triggers seizures, which can be achieved by various mechanisms. By acting on ion channels, such as voltage-dependent calcium ions, as in the case of ethosuximide, or on chloride ion channels in the GABA-A receptor, as in the case of phenobarbital, or alternatively, by inhibiting the release of the excitatory neurotransmitter glutamate through exocytosis, as in the case of levetiracetam. In phenobarbital, the carbonyl, which is part of the urea fragment, can be replaced by a methylene. and various nitrogen substituents have been used with the idea of reducing adverse reactions, specifically of the sedative type. Here are some examples. In primidone, the carbonyl has been replaced by a methylene, which can be converted to phenobarbital by metabolic oxidation. Mephobarbital and etrobarb are examples that present substituents attached to the nitrogens of phenobarbital, and it has been reported that their undesirable activity as sedatives is less than that of phenobarbital. We can see ethosuximide as coming from structural modifications of phenobarbital. First, the contraction of the 6-membered ring to 5-member ring generates the antiepileptic class of hydantoins, where phenytoin stands out. And by replacing one of the nitrogens with a carbon, we obtain the succinimides, where ethosuximide stands out. For levetiracetam, we can consider the substituted butyrolactam as the pharmacophore, where R1 corresponds to the butyramide substituent, maintaining the stereochemistry present in levetiracetam. And the carboxamide group is considered necessary for its activity, as we can see in these examples. And the substituents in R2 can be an alkyl group, as in the case of brivaracetam, or a phenyl substituted with an azide group, as in the case of this experimental drug. The 3 drugs are included in the World Health Organization list of essential medicines. Phenobarbital was patented by Bayer as a sleeping aid. Its activity as an antiepileptic was discovered by chance, and it was introduced by Bayer under the brand Luminal. The synthesis of Ethosuximide was reported by researchers from the Imperial College of Science and Technology. It was launched for the treatment of epilepsy by Park Davis, now Pfizer, under the brand name Zerontin. Levetiracetam was patented by USB and introduced by USB under the brand Keppra. The 3 drugs are used for the treatment of various types of epilepsy. The 3 drugs have good oral absorption and can be administered by other routes besides oral. The half-lives of phenobarbital and ethosuximide are especially long. In general, antiepileptic drugs can present severe but rare reactions, which require medical surveillance. Here are some relevant physicochemical properties of the 3 drugs. The retrosynthesis and the resulting synthesis will be presented in the following videos. Thank you for your attention.